Good morning, everyone, and welcome to MAE 209 Probability and Statistics. My name is Richard Kohar, and thank you, everyone, for tuning in on this Monday morning. Hopefully, you can hear me okay in the chat. Give me a thumbs up. Excellent. So, without further ado, here we go. Today's lecture is number 6, Elementary Combinatorics 2. We're going to finish up that section, and we'll finish up, and then we'll move on to conditional probability. Okay, for some reason, though, I'm just having a bit of overload, though, on the streaming. Okay, let's try this. So we talked about previously about permutations, and that's where the order does matter. In this case, we're going to now talk about unordered subsets, and that's called a permutation. Now, with this, we have a notation, which we call a binomial coefficient. And the formula for that is it's n factorial over k factorial times n minus k factorial. So here's an example. There are 25 cadets. How many clubs can be formed with 3 members? So the way that we would do that is this would be 25 choose 3. So there's the total number. And over here would be how many you pick. Okay, so that would be then, we would have 25 factorial over 3 factorial. Then it would be 25 minus 3 factorial. Is everyone okay so far, what I've done? So 25 minus 3 is 22. Okay. And just simplifying this. And I have 24 3 times 2 is 6. So dividing that into here, that gives me 4. So then I have 25 times 4, which is 100, times 23. So that's 2300. Okay. Just so that's the number of clubs that can be formed with 3 members from 25 cadets. Okay. So let's do another example. Let's suppose you have an iPhone and you're going to create a music playlist, and it contains 100 songs, 100 of which are by The Weeknd. What is the probability that one of the first 5 songs is a Weeknd song? So the way that we would do that is we're going to calculate the probability. We should calculate, first of all, this is the number in the sample space. So the number that's in the sample space, well, we know that there's 100 songs, again, total number of objects. So over here, 100. And we're going to choose 10. Okay, so now what we'll do is we'll take cases. We have that the first song is a Weeknd song. So what we'll say is that there's one that we'll pick at the beginning. So there's one. And then what remains is that, so let's say here is The Weeknd. And then, so there's the multiplication. We have to pick, well, we'll have 99 songs left over, and we'll have to pick, so the playlist is 10. So we have one that's already here, and over here, we'll have to have 9. So that's how many we'll have for the first song. For the second song is the first Weeknd song to play, which means then that I'll have to have one Weeknd song, and that will be in position 2. But that still means then that I'll have to pick, I really don't care what the order was for the other ones then. So what I'll have then is there'll be 98 songs to pick from. And we'll have 9. And we just keep going on, so forth. We'll have 97. Does order matter in this formula? No, the order doesn't matter. Okay. So we get the fourth one. So we had 97, now it's 96, choose 9. We'll have 95, choose 9. And so putting it all together then, No, it's just whatever the first weekend song is. So we don't really care. It has to be just, we know for sure there's going to be one of them that's going to be played, and then the rest of them. So for instance, let's say the fifth song is a weekend song to be played. What I'm saying here then is I'll pick one of those. So one of these will be fixed. We pick a song for this one, this one, this one, this one. We'll know for sure. And then this one will have to be a weekend song. And then basically one of those songs. So we fixed each of those. And then the remaining will be So putting that together, we get 99, choose 9, plus 98, choose 9, 97, choose 9, the 9 is because one of the songs has to be a weekend song. So that's how we'll do it. Why is it staying at choose 9 instead of going down? Well, because what they're doing is they're fixing the song at the position so that'll occur. So the first position, there would be one song that would be you would have, and then the rest would be, so there's 99 songs that you would pick afterwards. You would have the first and the second song, but you have to pick the remaining ones to be a non-weekend song, but you can't have, you're going to pick a weekend song and then a non-weekend song, so then you're left with 98. So that's why the top one is going down, but the number of selections stays the same. Okay. Isn't the question all the first songs? No. No, the question says, no, it doesn't say all, that one of the first 5 songs is a weekend song. So the way that we're doing that is we're taking then cases. Each case then is mutually disjoint or mutually exclusive. And so again, here's the first song is a weekend song. So that's, and then we don't care what the rest of them could be. It could be a weekend song on the second one. Or we have the case where the first weekend song to play is on the second one. Okay, perfect. What was the point to pick 9 weekend songs? No, the point was then we had 10 songs that were by the weekend, but there's 100 songs in total. Okay. And maybe, let me just double check then. So, moving on. Down. Here's another exercise. So maybe this might be a little bit more straightforward. So that example is from the textbook. Let's use this exercise instead. This might help. Exercise 38, this is from section 2.3. And we'll say that there's a box in a supply room, contains 4 40-watt light bulbs, 5 60-watt bulbs, and 6 75-watt bulbs. Suppose that 3 bulbs are randomly selected. What is the probability that all 3 of the selected bulbs are rated at 75? So what they're asking for is, what's the probability all selected are 75 watts? So in the denominator, which is the total number of ways we could select something, there's 4, 5, and 6. So 6 and 4 is 10, and 5. So there's 15 in total. There's 15 bulbs in total. And we're going to pick 3 of them. So this is the total number of ways that we can pick. It's 15, choose 3. Now this one says, what is the probability that all 3 of the selected bulbs are 75? So there's 6 75-watt bulbs in total. So we know that we want to pick from 6. We have to pick 3. So what I have is 6 choose 3 over 15 choose 3. And we can pull out a calculator. So I have 6 choose 3 is 20 over 15 choose 3. $455, which works out to 0.044. So is this part okay? Everyone following along on that exercise? Then part B, it says, what is the probability that all 3 bulbs have the same rating? So this is where I'll have to have cases. So again, and just a second. Okay, so for this, we have that, again, the same total, which is there's 15, and we're going to choose 3 bulbs. What we're going to use is the sum principle now, because we're going to have cases. There's going to be 3 cases. So over here is the OR. Question, how did we get 455 in the denominator? I used the calculator for that. So that's 15 choose 3. So 15 choose 3, 455. Okay, so over here we're going to have the 1, 2, 3 cases for this. So for the first case, we're going to have where it's all the same rating. So it's going to be 40 watts. So there's 40 bulbs there. We're going to choose 3 of them. So that is, I'll use a different color here. This is the case where it's 40 watts. Over here, we're going to have the case where it's going to be 60. So there's 5 bulbs. We're going to choose 3 of them. So that is 60. And lastly, we have 6 bulbs for 75 watts, and we're going to pick 3 of them. So there's our 3 cases. We can have 40 watts or 60 watts or 75 watts, where they're all the same bulb. So again, we have the denominator, it's the same one, so I know that this is 455. And I'll pull out my calculator again. So I have 4 choose 3, so 4, and I'm going to choose 3, so that gives me 4, plus 5 choose 3. 10, and 6 choose 3 is 20, so 34 over 455 gives us 0.0747. Okay, and what is the probability that one bulb of each type is selected? So yes, we're picking one of each type. So again, in the denominator, there's 15 choose 3. But now up top here, we'll use the multiplication principle. So we know that for the first bulb, let's say that, and the order doesn't matter, so for the first bulb, just pull up the page again. We'll say that this one will be 40 watts. Well, there's 4 options for that. And then for the second one, we'll say that it's 60 watts. So there's 5. And there's 6 for the 75 watt. So again, down below here, I know that this is 455. 5 times 6 is 30, times 4 gives me 120. And 120 over 55 is 0.2637. And lastly, suppose now that bulbs are to be selected one by one until a 75-watt bulb is found. What is the probability that it is necessary to examine at least 6 bulbs? So to examine exactly one, a 75-watt bulb must be chosen first. So there's 6 ways to accomplish this. To examine exactly 2, we must have another wattage first and then a 75-watt. So following that pattern, there would be, so let's just say, okay, I'll take some first. So there's 6 bulbs, so there's 6 ways to do that. If you have the 75-watt bulb, the first one selected on the second, there would be going back here, there would be 4 plus 5, there would be 9 other bulbs that you would pick from, and then you would have 6 to choose from on the second one. So there would be 9 on the first one, and then we select 6 on the second. For exactly 3, there would be 9 to choose from, and then 8 on the second. So again, we're picking from that one. And then on the third try, we would pick from this this 75 watts. So that would be 6. For the fourth, you would have, again, 9 bulbs to pick for the first one, and one of those would be used up. On the second one, you would pick from those remaining 8. On the third one, you would pick from the remaining 7 left over, and then we would have then the 75-watt bulb, and there's 6 of those. Here's the 5th. And again, you would have 9 of the 40 or 60 watt bulbs. So those are the non-75 watt. And then lastly, you would have 6 left over. So the probability that you would have to examine at least 6 bulbs, that's equal to 1 minus the probability of you examining five or less. And that's equal to you examining 1 or 2 or 3 or 4 or 5. So you could have the probability of 1 or 2 bulbs, or all the way up to 5. Which we've done over here. So over here we would have, for 1, we have 6 ways. And out of the total, there would be 15 bulbs. So there's 15 bulbs in total. So you would have 15. For the second, you would have 9 times 6. And in the denominator, there's 15 bulbs to choose from. And so there's 15 for the first one, and for the second one, there would be 14. So this is for the 1, 2. For 3, there's 9 times 8 times 6 over 15 times 14 times 13. So 1, 2, 3 for the fourth one. So we just copy from here. 9 times 8 times 7 times 6. 15 times 14 times 13 times 12 plus and the last one. So 9 times 8 times 7 times 6 times 6. And passing it through the calculator, what you will get is 0.21. That's a good question. How do you know when to choose? Where did the 9 come from? Okay, so I'll just answer that first question. How do you know when to choose the proper method between the product rule or the n choose k method? It depends on the it really depends on the product, or sorry, it really depends on the problem. But I would say that with the product rule, it's almost like sequential decisions. So you pick one, and then with the product rule, you'll have some numbers here. You'll have choices, but it's almost sequential. So for this first one, you would be again specifying, okay, a certain number, and the multiplication is the and. So you've done your 3 choices, you picked one of them, and then you did something else. Now you have something for the second one, say 2, and then 1. But that's what the product rule is. It's more like sequential choices. You're picking one as you go along. Whereas if you're using the n choose k, the order doesn't really matter. I'm just doing it all at once. I'm not so concerned about what order I'm doing it in. As for the 9, so going back up here, there's 6 75-watt bulbs in total. And over here, so the way that we're getting 9 is that there's 4 40-watt bulbs, and there's 5 60-watt bulbs. So that makes 9 in total. So these are 9 non-75-watt bulbs. Is that what you were asking about for the 9? Okay. So when you picked on the first, you said that the first bulb is 75 watts. There's 6 ways. If there is, again, if you're going to pick the 75 watt on the second one, okay, there it is. You're going to have it on the second choice. But on the first one, there's going to be 9. And so again, here's the third is going to be 75 watts, but you're going to have the non-75 watts here. So there's 9 on the first choice, and then you have picked one, and then there will be 8 left over on the second choice. And that continues for the fourth one and the fifth. So here's another one. This is in the exercises. It says show that n choose k is equal to n choose n minus k. So what I'll do is I'll start from the right hand side and I'm going to go to the left. So n choose n minus k. So you could write 9 ways times 8 ways. Yes, exactly. So I'm going to apply my rule. Wish I had, where's my little card? So again, just recall that we had n choose k is equal to n factorial over k factorial over n minus k factorial. So that's our formula. So in this case, we would have, there's n factorial over, in this case, the k is n minus k, so n minus k factorial. Then I would have n minus, in this is the minus n minus k factorial. So I would have n minus so n minus n, and then I would have minus gives me the plus k. And I can change the order. Oops. There we go. So we've shown it algebraically. There's another way we can think of it as combinatorically. So we can say that n choose k is equivalent to, maybe I'll write this a little bit better. Maybe I'll say this in a little bit more words. Switch pens. So let's say selecting k objects from n total objects, it's equivalent to not selecting n minus k objects from n total objects. Do we write QED at the end of proofs in statistics? You can. So let me just kind of illustrate that. So combinatorically is a proper convention. It's a bit dated now. Most people will just have like what we call like a tombstone, which is like a little square at the end. Basically just to show that the proof is finished. So just as an example here, I could have 5 choose 2. So I could say that there are 5 apples. So I could have, or let's say 5 stars, 1, 2, 3, 4, 5. So I could pick 2 of them. It's equivalent to not picking 3 of them. And if you don't believe me, we can actually show that. We can calculate that. So there's 5 choose 2. 5 minus 2 is 3 factorial. So I'm left with 5 times 4, which is 20, divided by 2 gives me 10. And similarly, I have 5 choose 3. I'll have 3 on the 3 factorial and 2 factorial. So again, same idea. Which gives me 10. So what we call this is the symmetry property. So going back to one of the questions that we had, someone was asking, how do you know when to choose the proper method between the product rule or the n choose k? And again, it all depends on how you count. I know that's not very satisfying, but counting problems can be solved in different ways. If you count the same objects in 2 different ways, then those 2 ways of counting are equivalent. This is the basis for what we call combinatorial proofs. So here's a proof. I'm going to say, suppose Subway has n toppings to build a sandwich. How many ways can you order a sandwich? So for solution 1, like our friend here has asked, let's use the product rule. So for the first topping, it can either be on or off. So you could have either tomato or not. So let's say, so there's actually then 2 choices. So it's either on or off. So that's 2. And there's your and.
You can have a second topping, and it can too also be on or off. So there's two choices for this. And then for the third topping, it can be either on or off. So there's two for this. Dot, 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 going on and on and on. I'm not going to write, because I don't know what n is. I'm going to say that n has to be an element of the whole numbers. So again, if we get to the nth one, it too can either be on or off. So there's 2. So I have 2 times 2 times 2 times 2 n times. So what does that equal? In the chat, what is it equal to? And it gives me a moment to have a coffee sip. Two to the n, perfect, yes. Yep. Because again, this happens n times. 2 to the power of n. Okay, so there's one way of doing it. I did it with the product rule. Here's solution 1. Solution 2. I'm going to use combinations. So here's a different way of going about it. Let's say that I have, okay, so I know that there's n toppings, and then I pick 0 of them. So in this case, that's no toppings. So this is the total toppings. How many I picked. And now I'm going to do, could have 1 topping. In this case, I could have, so there's n, and I'm going to pick 1 of them. I could have n toppings, and I pick 2 of them. Here's the question, what should I use in between these? We should use a plus, yes. Because it makes sense for us. We could have no toppings, or 1 topping, or 2 toppings, or 3. All the way up to, we can have n toppings, and we pick all of them. So that's all the possible ways that we can do it. So what we've done is we've counted toppings in 2 different ways to construct a sandwich. So since we counted the toppings to form a sandwich, in two different ways, therefore, n choose 0 plus n choose 1 plus n choose 2 dot 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 all the way up to n choose n is equal to 2 to the n. And there's our formula. We have a formula right there. And this is considered a proof. We call this a combinatorial proof. We've come up with a way or a story or some situation in which we have the objects and we show how we can count them in two different ways. And if they're the same objects and we ensure that we have the same number for each, then they're equivalent. So let's give me a moment then and discuss something called Pascal's triangle. So Pascal's triangle, I can start to form a triangle by, I start on the zeros. So I have 0 choose 0. There's only one way to do that. I have 1 choose 0 and 1 choose 1. That's 1 and 1. I have 2 choose 0, 2 choose 1, 2 choose 2. Okay. So I can actually form a triangle. 1 and 1, 1. How am I getting the next row? Let's say I want to complete, say, 6. Well, I know that along here, it's down the diagonals, it's always going to be, say, 1. To get the next one, what we'll do is we just add the two numbers above it. So 1 plus 5 gives me 6. 5 plus 10 gives me 15. 10 plus 10 gives me 20. 10 plus 5 gives me 15. And 5 and 1 gives me 6. You can see then the symmetry, which we had already talked about. So if I draw a line down here, you can see the symmetry. You can see then that, say, 6 choose 2 is equivalent to 6 choose 4. So you can see that it's 15 and 15. 6 choose 1 and 6 choose 5. That's 6. I can also tell you that from our previous proof that we just did, that if I sum up the row of them, it should equal 2 to the n. So if I took, here's a different color here. If I took the 6th row here, I add them up, that will equal 2 to the 6. And lastly, I'll just illustrate on here. This is how we get the next number. That's what we call Pascal's theorem. So in general, that would be, if I have n choose r, oh sorry, maybe I should be using k. That's what the textbook is using. So n choose k, n k plus 1. So that's what I'm doing. So I'm starting out on the same row, but my choices are increasing. So n choose k plus n choose k plus 1. I go down to the next row. So that would be the next row, and I still keep the same number there. So that's Pascal's theorem. So what I'm getting at is that it sometimes is quicker to have a triangle like this written out, and we can quickly look up numbers such as this, and they're very quick to calculate. Even for maybe 4 or 5 rows, is to sit there and, such as this, and you can sit there and calculate a couple of rows. So on and so forth. How many people had seen Pascal's triangle before? Yes, yes, okay, good. Perfect. I think now is a good time to take our 10-minute break. What would negative numbers look like in combinatorial form? There are some formulas to handle negative numbers in combinatorial form, but that's beyond the scope of this course. Okay, so 10-minute break, and then we'll move on to conditional probability. Sure. So looking at the weekend question, I'm not sure why we started with 6. The light bulb question. Okay. So for part A, there's 6. So we want to have all 3 of them to be the 75 watts. So there's 6 75-watt bulbs to pick from. Choose 3 of them. Over here, there's 15 bulbs in total. There's 4 40-watt. There was 5 60-watt. And there was 6 75-watt. That gives you 15. From that, you're going to choose 3 of them. So up here, these are all the things that we want, which is all the bulbs are 75. And in the denominator here, this is all the possible ways. So there's 15 bulbs in total, and we're going to choose 3 of them. Does that answer the question? For part D, why did we start with 6? Okay. So for part D, we started with 6 because it says suppose that the bulbs to be replaced one by one until a 75-watt bulb is found. What's the probability that it is necessary to examine at least 6 bulbs? So what we have is, this is what we're required to find, that at least 6 bulbs are required. And what we're going to do is we're going to use the complement. We're going to take 1 minus, and we're going to examine 5 or less, which means that it's 5 or less, so that would be 1 or 2 or 3 or 4 or 5. And so again, I need to calculate the probabilities for 1 bulb or 2 all the way up to 5. So for the first one, maybe I'll switch to a different color. There's 6 ways. So this is saying that on the first bulb, so again, it's selecting one by one. So that means that you would keep picking from the bulbs until you found one. So you stop immediately. So this means that on the first bulb that you pick, you actually were successful and you picked a 75-watt bulb. And there's 6 bulbs that are 75 watts. And that's what we're told in the question. So there was 6 75-watt bulbs. Does that make sense? Yes, that's right. So on the second one, you got the second bulb was 75 watts. So again, there was 9 bulbs. So there's 9 choices. So 9 non 75 watt bulbs, and then you were successful on the second one. That's right. So if I kind of highlight it. Okay, so resuming our lecture, we have conditional probability. So the idea of conditional probability stems from the idea that if you have more information, then it's to your advantage to use it. So again, if you have more information about something, you incorporate it. You don't just ignore it. Conditional probability is a measure of the probability of an event occurring, given that another event has already just occurred. So, let's say for any 2 events. We'll say A and B. We'll say that the conditional probability of A given that B has occurred is, so we use the probability and we'll use A, and then there's a line here that means given that B. So the probability of A given that B has occurred. So it's the probability of both of them occurring. So probability of A and B over the probability of B. And this is provided that, again, to keep this defined, make sure that the denominator, or the probability of B, is non-zero. So in words, what I could say then is that it's the probability of A and B occurring over the probability of B. So just to illustrate conditional probability, let's say that the probability that any given student in a classroom has a sore throat on any given day may be 0.05 or 5%. But suppose that we know that the person has COVID-19. Well, we would expect that they would be more likely to have a sore throat. So the probability of a sore throat without any information more than that is 0.05. But if you add that additional information, you tell me that they have COVID-19, well, the probability that they have a sore throat, given that they have COVID-19, can be much more higher, say 0.75. So let's say with probability 0.75. So what we're trying to illustrate here is that your probability of something happening can change if you have more information about it. Given that somebody's sick, they're more likely to have a sore throat than not telling me at all if they're sick or not with COVID-19. So let's do another example. Suppose that all customers buying a digital camera, 60% include an optional memory card in their purchase, 40% include an extra battery, and 30% include a card and battery. So we'll consider a randomly selected customer who buys a camera. We'll let A denote the event that a memory card is purchased, and we'll say that B is where a battery is purchased. And we'll give these probabilities here. We have the probability that A, so the memory card, we were told is 60% or 0.6. We have B, which is the battery. We're told that they purchase it with a 0.4 or 40% probability. And the probability that both are purchased is 0.3, or we could say that P, A, and B is 0.3. Here's the question that we have. Given that the selected customer purchased an additional or an extra battery, what is the probability that an optional memory card was also purchased? So it's very important the way that we've read it. This is conditional. But the order does matter in which we're putting it. So given that select has an extra battery, so we're given that information. We're told that they bought a battery. What is the probability that an optional memory card, or A, was purchased? So it's the probability of A given that B. So to calculate this, the probability of A and B over the probability of B. And we have 0.3 for the probability of this both occurring over 0.4 So 3/4, or that's 0.75, or you can say that's 75%. So we can say then that the probability that an optional memory card was purchased, given that the customer purchased an extra battery, is 75%. And this one says, given that the selected customer purchased an optional memory card, so here I'll set up my conditional probability, and this one says, given that they purchased an optional memory card, so in this case it's A, what is the probability that an optional battery? So it's the probability of the battery given that a memory card was purchased. So we have B and A over A. Now, B and A is the same as saying A and B. Just as a little side note, A union B is equal to B union A, and A intersect B is equal to B intersect A. So the union and the intersection are commutative. So again, we just substitute in our values. We have 0.3 over A, 0.6. So I get 3 over 6, or a half, or you can think of that as 0.5 or 50%. Here's something else to just remark. Notice that the probability of A given B is not equal to the probability of B given A. Okay, the order in which you write that is important. So that is important. Moving along, here's another example. I might have to. So here's an example. A newspaper publishes 3 columns entitled Art, Books, and Cinema. So we're going to call this Art A, Books B, and C for Cinema. The reading habits of their audience with respect to these columns are the following. So we'll say that. Oh, sorry, I just see a question now. In interpreting the probabilities, would the company want the customer to buy the extra battery first? I think that no, because the purchase is all being done at once. But what they're more likely to, what they're interested in, say for instance, they're more interested in in interpreting the probabilities, would the company want the customer to buy the extra battery first? No, it's not necessarily about a matter of buying it first or second, again, because it's just a purchase, it's all at once. But it's, for instance, you tell me that they purchased a battery, what's the probability that they likely bought a memory card? Well, you've told me that they bought a battery. There's a 75% probability now that that person also bought the memory card. But if you tell me something different, let's say that the person then, you tell me that they bought the memory card, and you then ask me what the probability of them buying the battery is, then it's 50%. Okay. I hope that answers the question. So we have this newspaper, and we have all this data here, and we'll start to fill this in. So what I would do is I would start with the last piece of information here. We say that 5% read all three columns. So I would say, let's say 0.05. Then the next one is that I have 13% read books and cinema columns. So I need to have it add up to 13. So 13 minus 0.05, that gives me 0.08. So again, 8 and 5 gives me 13. So again, that gives me the percent. So I've done this one. Moving up, I have 9% read the art and cinema. So this is this region right in here. And that's 9%. So 0.04 and 0.05, that adds up to be 0.09 or 9%. Then we have the region where art and books, so that's 8%. So that would be 0.03. So 0.03 and 0.05 add up to give me 0.08 or 8%. Then we have the cinema column, so they have to add up to give me 37. So 0.20. So 0.2 plus 0.08 plus 0.05 plus 0.04. That gives me 0.37 or 37%. For the books, I have 23, so I need to take away from 23 16. So 23 minus 16 gives me 7 or 0.07. And lastly, I have 14% for the art. So 0.04, 0.05, so 8, 12. And I need to take, so 14 minus 12 is 2 or 0.02. So this is also a good review of our Venn diagrams as well. But so we have, what is the probability that a randomly selected reader reads the art column? So it's the probability of A, given that the reader reads the books column. So this is the probability of A and B all over the probability of B. So you can think of this as, here we have A, we have B, we have C, we have A and C, or sorry, A and B, A and C, B and C, and over here is A and B and C. So what we want is the intersection. So A and B, so that's in through here, or this one, which is 8%, so it's 0.08 out of B, which is 0.23. And bringing out a calculator, I have 8 over 23 gives me 0.3478. So that's the probability that a reader is reading the arts column, given that they read the books column. This one says, what is the probability that a randomly selected reader reads the art column, given that the reader reads either the books or the cinema column or both? Okay, so they're reading the art column. So this is the art. We have that magical bar here, which is given that. And here we have the reader reads either the books, or the cinema, or both. So that's what that means. B union C. So that's either the books or the cinema or both. So what we can do here is we'll have A. So it's A and the second event here. So A and B union C. All over. So very similar again. It's conditioned on this event. So the probability of B union C. So let's see. Let's say that okay, so we need to do B union C, so it's everything in here. B. Or in C, so we'll just color this in as well. So it's all of those values in there. So you have 0.2 plus 0.04 plus 0.05 plus 0.08 plus 0.03 plus 0.07. And that gives you maybe I should have used, maybe I'll use some green because that's what I used for the event here. So on the denominator, what I get is 0.47. In A, so I need to then calculate what the probability is of A intersect this union here. So I have the part where it intersects is this part right through here, this region where it's cross-hatched. So in this case, I have 0.03 plus 0.05 plus 0.04. That gives me 0.12 over 0.47. Which gives me 25, roughly 25.5%. And lastly, we have the probability of what is the probability that a randomly selected reader reads the art column, given that the reader reads at least one of the columns. So at least one of the columns means that it's either A union B union C. So that's A intersect this event right here. So A union B union C all over the probability of A union B union C. And so, let me just quickly explain here. So I have ABC, and it's going to be the union of ABC. So it's everything in A, B, C. And we're going to intersect that with A. So we just cross-hatch here with A. And so what we're left with is all the area where it's cross-hatched, which means that the A intersect A union B union C, we can actually just simplify that down to just A. It's just A right there. Plus A union B, union C. So that probability is 14%. 0.5% or 0.14. I just see hello in the chat. And now we also have the union. So we can you can use either the principle of inclusion or exclusion, right? So one way to do that is you could sum these up, subtract the two-way intersections, and then add the three-way intersection back in. So let's do that. You can do this very quickly. So again, like I said, you sum up the individual probabilities, you subtract the two-way intersections and add back in the one-way intersection, and so you would have 49%, or if you don't believe me, you can go back in, add up all these individual probabilities that we've calculated here. So 0.02, 0.03, 0.07, 0.05, 0.04, 0.08, and lastly 0.2. And there is 49. So I have 0.14 over 49. Let's change that. I'm going to divide that, which gives me 0.2857. And lastly, we have D. What is the probability that a randomly selected reader reads either the art or the books or both, given that the reader reads the cinema? Okay. Again, the order matters. In this case, we're asked about, so there's our given that. So there's kind of our given that. The reader reads the cinema, so I'll put C here. And this one says reads either the art or the books or both, so I'm using the union. So that's A or B or both. So we have the probability of the first event and the second event over the probability of the second event. So I know that it needs to be A union B, so there is A union B is right through here. And it needs to intersect with C. So the parts where it intersects is, so here's A union B. I wish I could, maybe I'll just kind of, so here's A union B. And then where it intersects with C, it's just right through here. So in that region right here, that's A union B intersect with C. So going back, I just need to read these three numbers here, 0.04, 0.05, and 0.08. It's like the mustache right here. So what I need here is 0.04 plus 0.05 plus 0.08 all over C, and C, the entire C is 0.37. So 0.04 plus 0.05, that's 0.09, plus 0.08, that gives me 0.17 over 0.37. And dividing that, I get 0.0595. What a distinguished gentleman. Yes, the Venn diagram has a mustache. So we have the multiplication rule. What I had said before was we had, let's say, A is equal to A intersect B over the probability of B. Okay. If I multiply this by the probability of B on both sides, what we get is what we call the multiplication rule. So it's the probability of A intersect B, so on the right hand side here, is equal to the probability of B times the probability of A given B. So our first example is, what is the probability that you draw two queens from a well-shuffled deck of cards? And this is without replacement. So what we'll say is that E is the event of the first queen, and F is the event of the second queen. Oh, and I can also do one more. Make sure that as I look back up at the formula, the other thing I can do is so in this case, I'm just going to write E So this is okay. I can write that. So the probability of E the event the probability of E in this case is there's 4 queens out of 52. And for the second queen, there would be 3 queens remaining because you've picked one of them. And there would be not 52 cards, but 51 cards left. So over here, I'm just going to write, here's the probability of E. And this is the conditional probability of the second queen, given that you picked the first. So I have 12 over 52 times 51. Which is 2,652. And if I divide that, that roughly works out to 0.0045. And that is all the time that we have for today. We'll pick this up in our next lecture. If you have any questions, feel free to send me an email at my RMC account. For those of you that have asked about, again, we can set up office hours or appointments. And if there's not any other questions, I assume that stacks. I don't understand stacks. Okay, everyone. Thank you, everyone, and have a great day.